Hey everyone, and welcome to The Hidden Layer. Now, if you're an engineer and you are just tired of all the hype around AGI, and you just want to know how to build smarter, more efficient AI systems right now, then you are absolutely in the right place. Today, we're going to decode a paper that gives you a practical, no-nonsense toolkit to do exactly that. Let's dive right in. So, the paper we're looking at today, well, it doesn't pull any punches. I mean, you can see the title. It's designed to make you stop scrolling because it asks the exact question that's on every single engineer's mind, even if we're maybe a little too polite to say it out loud in meetings. It just cuts right through all the noise. And this quote from the author, Michael Timothy Bennett, just perfectly captures the chaos, right? AGI has become this abstract ink blot test, where everyone just sees what they want to see or what they're afraid of. It's a total mess of hype and hope, and frankly, a few horror stories. Okay, so that is the real question, isn't it? Beyond all the sci-fi dreams and the philosophical debates, how do we, as builders, as engineers, actually move forward? Well, in the next few minutes, I'm going to give you a clear framework directly from this paper that you can actually use to think about and to build more capable AI. So here's the game plan. We're going to break down the paper's core toolkit. It boils down to 2 fundamental building blocks that pretty much every AI system uses, and then 3 master strategies for how to put them together. And you're going to want to stick around because that third strategy, that is the real game changer here. It's the one that directly attacks AI's biggest weaknesses right now, inefficiency and brittleness. All right, so let's start with the problem. The paper gives this absolutely brilliant name to the dominant idea in AI over the last few years, the embiggening. It's this core idea that to get more intelligence, you just make everything bigger. And you know what? For a while, it worked unbelievably well. I mean, think about it. GPT-3 was trained on a staggering 45 terabytes of text. AlphaFold 2 basically solved a grand challenge in biology by throwing an entire data center's worth of resources at the problem. The core idea, what this paper calls scale maxing, was just so simple. More is more. More compute, more data, bigger models. But here's the catch. We're hitting a wall. We're starting to see some serious diminishing returns. We're throwing exponentially more compute, more money, more data at these models, but the performance gains, they're getting smaller and smaller. That curve you see is flattening out, and that's a huge problem if scale is our only trick. So, this is the really crucial point. While scale maxing got us some incredible wins, and it really did, its downsides are becoming totally impossible to ignore. We're talking about nightmare-level energy costs, for sure. But even more importantly for us as engineers, these models are horribly sample inefficient. They need an ocean of data to learn something pretty simple. And that makes them incredibly brittle. They just fall apart when they face a situation that's genuinely new or even a little bit unusual. So, if just making things bigger isn't the answer anymore, what is? Well, the paper argues that we need to get smarter by really mastering the fundamental tools we already have. In fact, it boils down all of artificial intelligence into just 2 foundational methods. So the paper frames the entire field as this beautiful balance between 2 core ideas. On one hand, you have search. Think about things like A-star or complex route planning. It's incredibly precise, it's verifiable, it's interpretable, but it's also really slow and brittle. Then, on the other hand, you have approximation, which, let's be honest, is pretty much all of modern machine learning. It's fast, it's scalable, it's great with messy, real-world data, but it's unreliable, it's a black box, and like we just said, it's incredibly sample inefficient. When you look at them side by side, they're almost perfect opposites. So, what do you do when you have 2 tools with perfectly complementary strengths and weaknesses? It's almost obvious, right? You combine them. The path forward isn't choosing one over the other. It's about building smart hybrid systems that give you the absolute best of both worlds. And AlphaGo is the perfect classic example of this in action. It didn't win by just using a giant neural net. No, it used approximation, the neural network, to make a really good guess about which moves were promising. Think of it like intuition. And then it used search, a Monte Carlo tree search, to precisely and logically explore the consequences of those promising moves. It was this fusion, this combination of fast intuition and precise calculation, that allowed it to beat the best players in the world. Okay, so we've got our 2 tools, search and approximation. But how we combine them and what we're actually optimizing for, well, that's the next crucial step. The paper lays out 3 meta approaches, or you could think of them as guiding philosophies, for how to design intelligent systems. So, the first strategy is the one we already know and have been talking about, scale maxing. This is based on Richard Sutton's famous bitter lesson, which basically argues that in the long run, massive compute paired with very general methods is always going to win out over clever, human-designed features. The goal here is simple: maximize your use of available resources. All right, strategy number 2 is what the paper calls simp maxing, which is just short for simplicity maximization. And this is built on a really old idea, Occam's razor, the idea that the simplest explanation is usually the right one. In the world of AI, this means we should favor models that are elegant and compressive. So think of things like regularization, dropout, or the minimum description length principle. It's all about maximizing the simplicity of the model's form.
And now for that third strategy I promised you. This is called we-maxing, and it's based on what the paper calls Bennett's razor. Now, this is a subtle but really powerful shift in thinking. Instead of maximizing simplicity of form, like simp-maxing does, it focuses on maximizing the versatility of function. The whole idea is to make your system's built-in constraints as weak and as flexible as possible, which allows it to adapt to the widest possible range of situations.
And this is why W-maxing is so important. It's the direct antidote to the problems of brute force scale maxing. See, by optimizing for functional versatility, you are inherently, by design, optimizing for both sample efficiency and energy efficiency. It's all about designing smarter, more adaptable systems from the ground up, not just throwing more compute at bigger ones. You can actually see this kind of thinking in the push towards multimodal models that have to flexibly handle text, images, and sound all at once. So let's just put it all together real quick. You've got scale maxing, which is basically bigger is better, but we know it's inefficient. You have simp maxing, which is the simplest is the best, but that can sometimes be too rigid. And then you have Y maxing, the most flexible is the best. The only catch? It's harder to design. It actually requires more thought than just turning the compute dial up to 11. Okay, that's a lot of theory. How do you actually use this stuff? Let's translate this whole framework into some actionable advice that you can literally take back to your team tomorrow. Here are the key takeaways. It's really this simple. If you're building a system that absolutely needs to be precise and verifiable, like for logistics or complex planning, you should lead with search. If you're dealing with messy, noisy, unstructured real-world data like images, audio, or text, then Approximation is your go-to tool. But, and this is the big one, if you are aiming to build a truly adaptive, efficient, and autonomous agent, you need to be thinking in terms of hybrids and applying that WA-maxing philosophy. Your main focus should be on how to creatively combine these tools, not just on how to scale one of them. Ultimately, the core message of this paper is a pretty profound one. For years, the main bottleneck in AI was just raw compute. Now, that bottleneck has shifted. The new challenge, the new frontier, is intelligent system design. It's all about architecture, it's about philosophy, and it's about strategy. So, the era of pure ambiguing, it's really drawing to a close. The era of smart, hybrid, and efficient design is just getting started. So the real question is, with this new toolkit and these new strategies in mind, what will you build?